Okay, so here we are, week 6, lecture 2. We'll start with the definition of local section. A local section of a vector bundle V on M is a section over some open subset U of M. That is, S from U to pi inverse of U equals to V restricted to U. I mean, we'll just call it like that. So instead of U to V, we are restricting it to pi inverse U. Okay, it's a local section. So also the concept of U of X, which is a small map such that pi third S equals to I over U. Okay, so we denote the set of all local sections of V as a vector bundle V as by gamma V comma U equals to all the set of all sections, basically set of all local sections and by global section we mean the section that we defined above, which is globally defined, and I think that space works. And the global sections of all global sections by V. Cool. As usual, let's go to examples of these local sections. example is again on a trivial vector bundle. On a trivial vector bundle, we have set of all okay, you already saw it doesn't hurt, I feel. The sections of trivial vector bundle as seen earlier, the set of all global sections, all sections of trivial set of all global sections of trivial vector bundle as seen earlier are just a set of all smooth functions from M to Rk. And the zero section is also a global section. Is a global section for any vector bundle. That is fine. Now we will the exercise is that in fact show that any section S M to V is an embedding. In fact, Z is an embedding of M in V. Section Z is a that we will show soon, but what we want to show is proposition is that let pi v to m be a vector bundle, then vector bundle, we have some enumeration here. If S1, S2 are global sections of V, then S1 plus S2 is in the global section of V. Then we also have if S is a global section of V, then V, F is a smooth function on N, then Fs is in gamma of V, where we define pointwise multiplication and pointwise addition, and gamma V. Okay, and this sort of sets the picture for gamma V is a module over C infinity M. In fact, this is a projective module, and it is an algebraic with geometric way of defining vector bundles. Let's get to the proof. So the first thing is we define S1 we define So S1 plus S2, basically by S1 plus S2 basically as a local trivialization, this is just represented by f1 of x plus f2 of x, right? So locally this is smooth. Actually, this is indeed smooth because it is locally. This is just an addition of functions. Exactly. So this is okay. For smoothness, we take ratio for P in M. Choose an open set. choose an open set U in M containing P. Choose open set U containing P such that we have the local trivialization H V to U cross RK. What we want to show is that this is a smooth map. What we want to show is S equals to S1 plus S2 is smooth map. We want to show that S1 plus S2 S equals to S1 plus S2 is a smooth map. For P means you have the local trivialization this. Cool. Then okay. Then S is smooth. Come on, this word is little. S is if and only if H circ S restricted to U is smooth. Okay, this is local trivialization is basically our trivializing of VU to U plus RK. Then that. Right? I mean, in fact, this is just the same image as this one, sort of. Then H circ S underscore I of X is basically X comma Fix as a section of a trivial bundle. Then H O S of X is basically X comma 1 of X plus F2 of X. Which is smooth since Fi is smooth. Trivial bundle where Fi U to RK is smooth. the multiplication with f is pointwise, similarly pointwise, and it does have module structure over show us actually. Okay. Note that we had the following vector bundles. Two vector bundles, we saw two vector bundles over S1. We saw two line bundles over S1 and pi m to S1, the base bundle, comma pi S1 the trivial line. Proposition m and S1 are not isomorphic as vector bundles. Not even diffeomorphic. suppose H तो मुझे भूख लग रहा है। Okay, so suppose H, I mean, okay, wait. Suppose H S1 cross R to M is an isomorphism. Isomorphism, then H should take the zero section of let's solve V of S1. What the fuck? What the okay. Section of S1 to the zero section of S1. Yeah. But thing is, there is a neat argument that it cannot happen. For example, okay, take screenshot. T0 sections. T0 forwards. H of S1 S1 cross R minus S1 cross set 0 equals to S1 cross is disconnected. Disconnected is disconnected, whereas minus 8 is connected. Disconnected. Yep, I'm back. So we want to show that M minus A is connected. That is the Mobius strip with the central line removed. It is still connected. It is connected because in fact it is path connected. it is easier to see if you look at the following figure that I am going to attach soon. So yeah, it is in fact path connected, because when you look at the figure, this is path connected, and varying basis on fibers of vector bundle. Yeah, so we can talk about smoothly varying basis on fibers of vector bundle. So for that we introduce frames. So frames is an interesting concept. Yeah. Okay, before we continue, okay, cool. So let's talk about frames. Frames are a collection of sections that at any point will give you a basis on this fibers, right? So at each point you have a collection of sections, images of sections, and this collection forms a basis. So of course you need to have a k collection if your vector bundle of rank k. So that's exactly how we are going to define. Okay, before that I need to set few snippets, edit few snippets. So let's go to, okay, maybe let's do it from here itself. Dot snip dot sh. So what I want to do is I want to add a snippet for definitions, right? Snip def definition I begin definition, then 1, end definition, and then this is 0, then end snippet. I hope that's how things have been there. Don't want it to be automatic, but define, yeah, IA, no, not IA. Yeah, and the other thing is need to edit the cap wall apart. N, 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 N. Yeah, this has to be NN, and yeah, even the UU part, UUU part, UUU, I think UU is better. Big cup, big cap is NN, UU, NN, connected, okay, yeah. So these are some to get rid. And what else did I learn? So figure is done. Figure, yeah, figure. I need to edit the figure. What the hell is happening for the figure? Okay, so I don't want this bullshit here. I want a simple 2 here, three here, and then I don't want anything here. 4 here, 2, 3 and 4, and then I can change it later. Default is 0.5. So yeah, default is 0.5, and then 0. This should do. Okay, so review, restart. Sorry, oh shit, I see. .dg.sh, indeed. Okay, cool. Okay, now we want definition. The definition is that of the frames from a vector bundle from V to M be a vector bundle of rank K, and U in M an open subset if S1 K in the collection of local sections such that these at each point forms a basis of Vx fiber attacks for all x and u, then the collection S1 to Sk is called a local frame of V on U, right? Cool. So yeah, okay, right. Collection of sections is the form of this local frame on U. So the immediate proposition we have is, if a vector bundle is isomorphic to trivial vector bundle M cross Rk, I mean, in fact, a vector bundle is a trivial isomorphism if and only if there is a global frame on V, right? So the basis works for all of for all the fibers, for all the points in the vector bundle. Interesting. So let's see the proof. So the first part is basically simple. If M cross Rk is isomorphic to V is an isomorphism, then basically Si from M to the sections define these sections on the vector bundle V as through the diffeomorphism carry the, it's actually H inverse, I suppose. Yeah, sorry, that's right. We define sections on M cross Rk, and then you, using a diffeomorphism, you just send it to the V. So simple. Then S underscore 1 of x, comma S underscore k of x form basis. Simple. Yeah, I don't think further it's necessary. I see. So cool. Now if there is a global frame, yeah, the question is if there is a global frame, then how do you say that it's trivial? How do you say that it's trivial to us? So what do you say is let S1 SK be a global frame and gamma of V be a global frame. Then define yes, we want to define the diffeomorphism between the trivial bundle and the general bundle. Then define H from M K to V such that H of X comma C equals to S of you know that there is a section S from M to that, so S of X isn't that so? I see. How do I get this way? Equals to C1 S1 of X plus dot 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 plus C underscore K of X, which is basically in V underscore X. I see. Since C is a global frame, any element in V can be written as any element of Vx can be written as a. More precisely, C to this is a. So our claim is that this is a diffeomorphism. So then define this is a diffeomorphism. Why is it a diffeomorphism? Again, V is a locally trivial map. You can local thing. Then this is basically f1 of x This is basically x, it goes to x, and comma f1 of that, which is smooth. So this is a smooth map, and the inverse yeah 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 it's a global frame on V. So again it's a diffeomorphism from that. So anything in that can be written as this, and then the moment you write this you can just take the coefficient C. So now it just becomes okay, what we want to show is another diffeomorphism.
Yo, what's up? Jara?
Hello. Huh? So what you can do now is aha, yeah, indeed we are going to do it carefully. um, this so h from x k to v in x is a linear isomorphism the linear isomorphism Yeah, clearly that can be clearly seen, right? uh, this is clearly seen. That is something that you can clearly see. Now the claim is that H is a diffeomorphism. Claim H is a diffeomorphism. That will complete the proof of the vector bundle isomorphism. So yeah, H is a bijection. That is fine. Why is it a clearly bijection? Because anything can be written as this one, and then and so because it's a global frame, we're writing in global frame. So this when the moment that one is take. X of c, this is again the basis of x and c1 has to be equal. So that is done. It is clearly a bijection, and what we need to show that it is a smooth immersion. If it's a smooth immersion, then it is a diffeomorphism. Okay. It is clearly a bijection. I have to show, and it suffices to show that H is a smooth immersion. Why is it enough to show that it's a smooth immersion? I think we can go back and recall our diffeomorphism results where we have basically by inverse function theorem, locally you can invert it. So locally you will have a smooth function. I think follows from the inverse function theorem, right? Yeah, follows from the inverse function theorem. Inverse function theorem. Good. Yeah, indeed. So immersion. So how do we show that? So what we do now is let u comma phi be a chart of M such that Okay, is a trivialization. Okay, this is smooth motion. Let v 1.5 okay. So trivialization. Now we want to show that the differential of the h, the function h is yeah. So we want to show that h is a smooth motion. So that happens if the Jacobian of the transition function is non-zero, basically invertible, terminal Jacobian matrix. So it's time for a very nice image. It's a trivialization, and now we consider the what is this vbtr global frame dot jpg. There is a typo now, and then we have caption. Or do you have the caption? I don't think we need any caption for this. So the trivialization, we okay. So this is the whole thing. Okay. Now this is getting a bit overwhelming at this point, but okay. So what? Let's just get back. We have a global frame of V. We have a linear isomorphism between a trivial vector bundle over M and the vector bundle we are talking about V. A linear isomorphism exists at each point. That is good. We want to show that it's in fact a diffeomorphism. So how are we going to do this? Of course, we want to go to the local chart of V. Locally it's trivial, so we have the trivialization G from V restricted to U cross RK, and in fact U cross RK, say you have also you have also the map H that you want to show it as a diffeomorphism. So eventually you end up with in two ways to phi of U cross RK, right? What you want to show is this map G. Is it whether its Jacobian is whether the matrix G is whether the Jacobian of the matrix is non-zero, so that can be invertible and injection and all that. Yeah, right. So we want to look for. Sorry, I've included the image. It's important that we load the image here. So we have the map, the capital G, right? We want the map capital G, but note the gray marked things. So basically you want the through the trivialization one can write g of si of x is exactly what I was thinking. S of x equals to x comma fi of x. Because it's a trivialization, it's basically given by the map the functions f from u to rk. This is the specialty of the trivialization. Wait, what the fuck? Wait. Why does it? Why is it fuzzy? Why do I feel fuzziness? What does the trivialization do a section? Say of x is a point. Right? Say of x is a point on the trivialization, then it's basically x of s. So exactly. Your section is actually from u to vu, right? S, yeah. There is s missing here, but then when you go to a trivialization, it's basically section and u plus rk, which is basically a function, a smooth function. Cool. That is fine. Where phi of x u to k is smooth. Now then g x comma c equals to x comma, yeah, so you have fi inverse of x. Okay, and then you, yeah, so some ci fi of phi inverse of x. It's a smooth map. Smooth. Smooth with the Jacobian of g at point x comma c equals to matrix begin. What the fuck? P matrix I and 0 star and Yeah, I mean, this is invertible because Fik is a linearly independent. Fi linearly independent. Whew, that is cool. So the remark is few remarks. Basically, any global frame, if you have a global frame, it is if and only if it's a field vector bundle with isomorphic to the trivial vector bundle, right? Cool. Some remarks. First thing is that any vector bundle is locally trivial. That is always true. So locally any section can be written as a function. Next, study the criterion for checking smoothness of sections via local frames. This is interesting. It's going to give us a very interesting result. I have pros if and only if Okay, so we are done. This is the third part of PG. So let's go. Well, next we'll start with smoothness criteria of vector bundles from the local sections. This is almost trivial because any smooth section can be written in terms of its local frames, and there has to exist some infinity coefficients of the two, right? And if there exists infinity coefficients, um, mm, yeah. So what you want to show exactly what this infinity functions coefficients are to define such a smooth section. So you you go and do all of that. Okay. What exactly is that? Basically, edge of speed and C. So that no, so that S of P is precisely A on B is one plane. Yeah, precisely. Precisely, precisely. Precisely. What we exactly established is that mm-hmm, locally, yeah. I mean, locally, HFPC is just the yeah. There's a canonical way to just define the basis of maps. So yeah, yeah. Yeah. Especially when you have a when you have a section, you can write it. But life is very easier when you have a section, and not just a section. If you have a frame, then you can write exactly what is edge. So this is interesting, right? So what we just did, it is indeed remarkable. Indeed remarkable that the local trivialization can now be written in terms of the local frames. In fact, this will give us a criterion for checking smoothness of sections by local frames. This is local property now. Local smooth function and smooth section T. Oh. Very interesting stuff. Cool. We will now end this session.